Okay, so let us continue our discussion on quantum theory of radiation. So in this lecture, we will try to deduce this Wien's distribution law, Rayleigh-Jeans law, Stefan-Boltzmann law, and Wien's displacement law from Planck's blackbody radiation that we have studied in the previous video. Okay, and during the course of this deduction that we will see, we'll realize that Wien's distribution law, which was successful in explaining or providing explanation for the blackbody spectrum, which was obtained experimentally for the shorter wavelength part. It was so the Wien's distribution law was successful in explaining or it fitted well for the shorter wavelength part, whereas the Rayleigh-Jeans law, which was successful in explaining the longer wavelength part of the blackbody spectrum, which was obtained experimentally. So we will see that these two laws are the two extreme cases of the Planck's radiation law. Okay, so let us start. Okay, so first let's try to derive this Wien's law from the Planck's law. Okay, so here is this we are familiar with from the previous video. This is Planck's radiation law or Planck's law, right, in terms of wavelength, which is given by the energy density is given by 8 pi h. H is a Planck constant, c is the velocity of the radiation, okay, by lambda to the power 5, and then d lambda by e to the power h c by lambda kt minus 1, right? Okay, for shorter wavelength, this expression, see, so we know that for shorter, if lambda is small, okay, so if lambda is small, what happens is h by lambda kt is a big number, or is a bigger number, right? Is big, okay, or large number. So when it comes to, if I take this as a power in the exponent, right, okay, so this h exponential of this term will be even bigger than that, so it will be much greater than 1, right? Okay, so since it is much greater than 1, so I can ignore this 1 which is present in the denominator, right, minus 1, because this expression, this term is way larger than 1. So if I ignore that, so I will remain with in the denominator of the expression e to the power h c by lambda kt. And if I doing that, if I just rewrite the same expression, okay, in the following way that is given here, right? So this way, and you realize this is your Wien's law of energy distribution, okay, which fits well for the lower wavelength side. Okay, right, all right. So this, like the condition, by taking the condition for the short wavelength, where this exponential term becomes much larger than this numerical value 1, then automatically this Wien's law comes into the existence here, right? Okay, so you can see the Wien's law from the Planck's law. Okay, now let's try to derive or deduce Rayleigh-Jeans law from the Planck's law. So which we all know that Rayleigh-Jeans law fits well the experimental data for the meaning the longer wavelength part, right? So now if your lambda is large, right, so if your lambda is large, so this term in the exponent hc by lambda kt is really small number, right? Because lambda is large, so it's c by lambda kt, this becomes small. So that means what? This e to the power h c by lambda kt will become even smaller, or meaning it will become a small number, right? Isn't it? Okay, so, and which will be like much less than 1, as it is written here, right? So I can have the expansion for this exponential, right? Series expansion for the exponential term in that. So if I take it only to the first term and ignore the higher order terms, so I will have only 1 plus this hc by lambda kt, right? So if I substitute for this expression in the expression of Planck's radiation law, so I need to substitute for this term 1 plus this hc by kt. So I have this, then this 1 and 1, it will get cancelled out. I'll remain with what? So from here, as it is written here, okay? So 8 pi hc by lambda to the power 5, and then I can I can take this up, so it will be lambda kt by hc, okay, which is nothing but, so this lambda and this one power can be right, cancel out, so it will remain with 4. So I will have the expression of Rayleigh-Jeans law, which we have studied in our previous videos. Okay, so yes, so this is the expression for Rayleigh-Jeans law, which we know that could explain successfully the black body spectrum, which was obtained experimentally for the longer wavelength part. Okay, so as you can see, that simply imposing the conditions of shorter wavelength or longer wavelength, we could derive the Wien's distribution law as well as the Rayleigh-Jeans distribution law from the Planck's radiation law. Okay, having learnt about the deduction of Wien's and Rayleigh-Jeans law, let us try to derive the Stefan-Boltzmann law from the Planck's law. Okay, what is Stefan's law? We have studied in one of the earlier videos, that which deals with actually the emission of black body, right? So the energy emitted by black body per unit area per second, or which was proportional to T to the power 4, meaning that like fourth power of the temperature. Okay, so we shall try to derive that expression here. Okay, from Planck's law. Okay, so it is written here that this law governs the total energy radiated per unit area per second, as I told you, by a perfect black body at temperature T. Okay, so the Planck's law gives you energy density for within the range of frequency, isn't it? So the total intensity we can calculate if we integrate over entire spectrum of frequency, or entire range of frequency. Okay, so the total energy density, so here energy is missing, so you can, so total energy density U, the capital U, inside hollow enclosure is obtained by, so if I integrate over all the over this energy density, which is meant for this U of nu, which is meant for only for the frequency range nu and nu plus d nu, right? So if I integrate over all frequency, I will get total energy density for all frequencies. Okay, which is what I will get from this expression. Now if I substitute this expression for the energy density in terms of frequency, this is the Planck's law, right? So if I substitute this, then this constant term will come out, right? So I will within the integration term, or the integrand, will have nu to the power cube by e to the power h nu by kt minus 1 d nu. Okay, now I have to make some substitution. Okay, so this is a bit of mathematics now. So if I take x equal to h nu by kt, d nu becomes simply this. Then substitute back in the integration, right? So u equal to, so this term will, constant term will come out, and then integration of x to the power cube e to the power x minus 1 dx. Now I will use some standard integral. Okay, so standard integral for this is given by, so the value of the integration is pi to the power 4 by 15. Okay, what do you have to do? Simply substitute the value of this integration, that is pi to the power 4 by 15. Then we almost we are into the Stefan's law, right? Because 8 pi h by c cube, all these are constant, k is constant, right? H is constant, t to the power 4 we already got in this. So, and remain this pi to the power 4 by 15, these are numbers, these are constant. So the total energy density, as you can see here, we can write that is proportional to t to the power 4. Almost we are into the Stefan's law. Okay, but Stefan's law deals with what? The energy radiated by the black body, right, per unit area per second, okay, which is proportional to the fourth power of the temperature. While deriving this Stefan's law using thermodynamics, there also we have arrived at this expression. But then we say that this U is what? The total energy present within the enclosure, that the total energy density present within the black body, meaning the enclosure, right? So this must be somehow related to the amount of the energy that a black body can emit, isn't it? So this U must be the total energy density must be proportional to the emissive power of the black body, isn't it? So there is a relation which we did not discuss at that point of time, but then for time being, just you accept this, that this E is the emissive power of the black body, okay, or the total energy of radiation that is present within the enclosure, okay, which is related to this total energy density. So E is equal to C is the velocity or the speed of radiation, okay, and U by 4, okay. So this is the relation, okay, which holds between this total emissive power and the total energy density present in the enclosure, okay. So if I substitute, so if I obtain U from here, so U will be what? 4E by C. And if I substitute this expression in this, because I need what here? Stefan's law deals with what? This emissive power and temperature, the relationship relation between this emissive power and the temperature, okay. So if I substitute back this one, so U, which as I told you, 4E by C, and all these constant terms, right? Nothing you have to do, you just copy and paste here, okay, and then take out this t to the power 4 aside, okay. So then again, just you do little bit of maths here. This will be 2, then 4, this will be 2, okay. So I will remain with this, and this constant term we can call it sigma, which is Stefan's constant, okay. And I will, so here I get back the expression what we are familiar with for Stefan-Boltzmann law, okay, which says that emissive power of a black body per unit area per second is proportional to the fourth power of the temperature, right. So here we have deduced the Stefan-Boltzmann law from Planck's radiation law, okay. We have one more law to derive, yes. So Wien's displacement law from the Planck's law, okay. What was Wien's displacement law? If you remember, this was lambda m to the power m, lambda m multiplied by temperature is constant, meaning what? Lambda m corresponds to the wavelength at which the intensity or the energy radiation by black body is maximum, okay, and then at some given temperature, okay. So if I multiply by the temperature with this lambda m, it becomes constant, and it had a certain value which we'll try to calculate here. So we need to derive this Wien's displacement law from the Planck's law, okay. So again, write down the Planck's law in terms of wavelength here, right. So as I said here, lambda m corresponds to the wavelength at which the energy emitted by the black body is maximum, okay. So for getting the maximum value of this expression, what you have to do? You have to differentiate this expression with respect to lambda, okay. Simple mathematics. Take out this constant term extra, then because I will have to use chain rule, because there are two terms as I can see here. So 1 by meaning I can talk about like this lambda to the power 5, there is one term, and then I can talk about, I can take e to the power ec by lambda kt minus 1, this I get, okay. This is second expression which I can do. So it's a product of two functions, let's say. So then I have to use chain rule, right. So if I differentiate this first term, so it will be minus 5, then lambda to the power minus 6, and I'll keep as it is like a constant. In the second term, plus it will be, I'll keep this term as a constant, and then I'll start differentiating this term. Here also I have to keep on going inside, I have to keep on using chain rule, right. So 1 minus will come out, right. So minus 1 by, actually minus 1 by this whole thing to the power 2, and then I have to differentiate again this inside, so which will be e to the power hc by lambda kt, and again because there is 1 by lambda, right. So hc by kt is constant, but there is this 1 by lambda inside, right? Inside 1 by lambda. So I will get minus, so there is one more minus will come out here. So minus lambda to the power minus 2, but this minus and minus will get plus. Okay, so eventually it will be plus. Okay, so I think you can do it yourself. Okay, so since there is this, then this term has to be equal to 0, right? So what you have to do there is, I can just shift. So this constant term anyway you can get rid of, right? Because this is never going to be 0. So the term, the expression within the bracket has to be equal to 0. So while shifting on the left and right, we get this expression. Okay, so here see, there is two terms. It's lambda to the power minus 5, lambda to the power, meaning see this plus, you should not get confused. Okay, this plus is meant for while deriving. Okay, so this, there will be lambda to the power minus 7. So I have written lambda to the power minus 6, and then one lambda is absorbed here. Okay, remaining the same. So if you look at this expression from the left and right, you can cancel out few things, isn't it? So this lambda to the power 6, it will go off. Then this entire denominator, I can go off with this 2, isn't it? Okay, I will have this side only 5. So, and then now since I know that, right, I was trying to maximize this expression for energy density, right? So I'm putting this lambda equal to lambda m, and so I substitute for, so wherever there was lambda, I just substitute with lambda m. So while doing so, I will have this expression, and then this as it is remain here, so this expression will be equal to 5. Okay, again make some substitution, which let's say x equal to, so this entire thing I call it x, right? So if I substitute back, I will get this x into e to the power x by e to the power x minus 1, which is equal to 5. Now these equations hold good, you can solve it numerically. Okay, so this equation holds good for value of x equal to 4.965. okay, so then I can substituting back again for the x, so I will get this expression. Now see, most of the things are constant here, right? So apart from what we need, so h is constant, c is constant, values are known, k is constant, Boltzmann constant. So I will have this lambda m and then multiplied by t equal to this. Okay, so this expression, first of all, this lambda m multiplied by t is constant, which is our Wien's displacement law, isn't it? And this value exactly becomes equal to what we had considered while studying Wien's displacement law. Okay, this constant value. So this is how we can derive or deduce the Wien's displacement law from Planck's radiation law. Okay, so in this video we have tried to deduce this Wien's displacement law, Rayleigh-Jeans law, then Wien's displacement law, and Stefan-Boltzmann law from the Planck's radiation law. Okay, so this brings to me end of this the quantum theory on radiation. Okay, so according to your syllabus, whatever topics were there within these two, classical theory of radiation, quantum theory of radiation, I think I have tried to cover all the topics. Okay, and in the next video onwards, we will try to have our discussion on quantum statistics. Okay, we will try to review some part of classical statistics, and then we'll start discussing on quantum statistics.